Welcome to Puzzles to Exercise the Mind, lesson number 7. At the end of lesson 6, I left you with this puzzle, and let me restate it here, then we'll talk about the solution on the next slide. So you're confronted with two doors and two guards, one guard who's a truth teller and the other guard who never tells the truth. Everything he says is false. One door leads to heaven and one to hell, and the puzzle is to find out which door leads to heaven by asking one of the guards a question. And again, we don't know which door is guarded by which guard, so that's an additional complication to the puzzle. We have 4 cases. I've showing them here pictorially. So we have the truth teller card, and we don't know whether he's guarding the gate to heaven or the gate to hell. So that's 2 cases. And then there's the untruth teller guard, and we don't know if he's guarding the gate to heaven or to hell. So the question is, which question do we ask? We could ask either one of these. We want to get a consistent answer because we don't know who we're talking to. So we want to get the same implied instruction from both of them, so that we know no matter who we're talking to, they're both pointing us the same way, which means either we do that or we don't do that. Either way, we have to figure that out based on our question. So there's probably more than one question. I'm going to talk about one possible question, and we'll go through the cases for that. We have the answer on this slide, or at least one possible answer. The question would be to ask, which door would the other guard say leads to heaven? I think if you asked if you replace heaven by hell, I think that also works. You might want to try that. But let's think through this particular answer here. So we have 4 cases. If the truth teller is guarding hell, so it's this one here, and if we asked the truth teller what would the other guard say is the door that leads to heaven, the truth teller would be honest and tell you what the untruth teller would say, and he would say that it's the door that the truth teller is guarding, because he's going to lie. So then if the truth teller is guarding the door to heaven, and you asked him what would the other guard say is the door to heaven, of course the other guard would say it's the guard that this untruth teller is guarding, and that again would mislead you. So in both of these cases, your best thing, what you should do is choose the opposite of the what's being given as the answer here. And then we go to the untruth teller, and let's say he's guarding hell, and you asked him, well, what would the other guard say? And the other guard would say he would lie and say the other guard would tell you to that it's the door that I'm guarding, which is is not true, but that's what the untruth teller would say. So again, you should choose the opposite door, the one that's being guarded by the truth teller in that case. And then if the untruth teller is guarding the door to heaven, and you ask him what would the other guard say, again he would lie, and he would say that the guard that he is guarding, which of course is in this case the door to hell. So that would again you would choose the opposite. So no matter even though you don't know who's guarding what, no matter what happens in any of these 4 cases here, you should always do the opposite of what's being responded to you. So that this would be the answer that would get you to the right place. So you can check it again. It's a little bit confusing because you're asking one guard what the other guard would say. This guard will always tell you the truth of what the liar would say, and that would misguide you. And then the same thing happens here. You ask the untruth teller what the truth teller would say, and he would always twist it to give you the wrong direction. So in all four cases, you're basically getting the misguided, and you should do the opposite of what's being given to you as an answer here. You might want to also try, as I say, that just replace heaven by hell. I think that also works as a solution. There's another tricky logic puzzle. This one might even be harder than the last one. It's a little bit confusing. And you need to use very precise logic here to get this right. I'll have a reference actually as part of the solution, but I guess I can mention it here. It comes from some test given in Brazil to public school students, I believe. So that's the source. It's certainly not easy, but let's look at what it asked. So assume the following two sentences are true. Pinocchio always tells falsehoods. And then Pinocchio says, all my hats are green. And then the question is, what can be deduced from the above two statements? So there's only one correct answer here. A, Pinocchio has at least one hat. Pinocchio has only one green hat. Pinocchio has no hats. Pinocchio has at least one green hat. Pinocchio has no green hats. So there's five choices, only one holds true. And again, what we're given are these two statements here. So we can't contradict these statements. They both have to hold up against the any possibility of what hats he may or may not have. These statements need to be true, and then only one of these statements is true, given that these two are also true. All right, so I'll let you think about that. You might want to pause the video, and then I'll give you the answer on the next two slides. So the first thing we'll do is eliminate some of these cases. Even here it gets a little bit confusing, at least to me, but I'll try to go through this slowly. So B, D, and E can be eliminated. Let's say Pinocchio has 3 green hats and 1 black hat. So that's what's actually happening here, right? So that doesn't contradict the statement here, because Pinocchio says all my hats are green, which is false in this case, right? He has 3 green hats and 1 black hat. And then this statement here, B, Pinocchio has only 1 green hat, is not true. So even though these statements are not contradicted by this one case that we're talking about here, so these hold true, but then this statement is false. So this is not one of the true statements. What about Pinocchio has at least 1 green hat? Well, if he had 3 black hats, again, he would be lying, so he would still be telling a falsehood, and that could be the reality that he has 3 black hats, but then saying Pinocchio has at least 1 green hat would be false. So this one gets eliminated. What about the E? Pinocchio has no green hats. Well, he could have in actuality 1 green hat and 1 black hat. So again, he would be lying, right? Because he has a black hat, and this could actually be an instance of something that happens without contradicting these two statements. But statement E is now false, right? Pinocchio has no green hats is a false statement in this case here. So B, D, and E, I'm not going to say they were easy to eliminate, but they're the easier out of the 5 to eliminate. So we're left with 2, and that's what I'll talk about on the next slide. Which one of these 2 is true and which one is false. Part of this is a bit tricky. We have 2 options left, A and C. Let's look at C. Pinocchio has no hats. This is the tricky part. So if Pinocchio has no hats, then the statement, all my hats are green, is vacuously true. This is something from logic. And I'll go into this a little bit more detail in a second, but taking my word for it that this is vacuously true. However, Pinocchio only makes false statements, so he must have at least 1 hat, in which case it's choice A that's the only true statement. Now let's talk a little bit about vacuously true. So let's say that you don't own any Rolls-Royce cars, and you say to somebody, all my Rolls-Royce cars are black. That's what's called vacuously true. You don't have any, so you're not lying. If you had any, then they would, then you would have you could be possibly lying if they weren't black. But since you don't have any, it's called vacuously true. And there's a little bit more in this YouTube video from Mind Your Decisions. He goes through the different cases as I do here. And the name of the video is Viral Logic Test from Brazil. I'll put the link in the description to this video. And he goes through a little bit more of this, in addition to explaining the puzzle, he goes a little bit more into truth tables and showing what it means to be vacuously true. Basically, the idea is if from a false statement you can imply anything. And that's the argument that he describes in his video. So I'll leave that to you if you're interested in getting more detail on that. This is a logic-based riddle, the Hat Riddle. My drawing skills are not great, so imagine these rectangles are people who are lined up, and they're all wearing hats, either black or gray. And A can see the hat colors of everything in front of him, and B can see the hat colors of what everyone is wearing in front of him. And these people here are given a challenge. For whatever reason, they're given a challenge to see if they can guess the color of their hat. They don't know the color they're wearing, so each person needs to guess the color of their hat that they're wearing, and under the conditions that each one can see the color of the hats of the people in front of them. The other thing that they can do is they can say the name of the color hat. So that's the test. They can A can say black or gray, B can say black or gray. That's the only thing the only other information they can give out. And the rule is that they can only get one wrong. So and they can talk beforehand, so they can strategize beforehand. And I guess the hint I'll give you is that they can only say black or gray. However, they can strategize before this challenge starts as to what black or gray means. So, for example, they could say that I'll say the color of the hat in front of me. So A could say gray, and A would already get the color of his hat wrong, unfortunately, and that's the one you have, you're able to, the one you're allowed to get wrong. So B would know, okay, I'm going second. I know A is going to call out the color of my hat. So I'll say gray, and that's fine. C may think that we'll follow what B says, and he'll just repeat gray. But now D is not able to, has to guess, right? D only has a 50% chance. If he follows, there's no way C could both say the color of his hat, which happens to be gray, and the color of D's hat. So that strategy is not going to work. There is a strategy that can work, but it's not saying the color of the hat of the person in front of you. So think about that. It comes from a TED Ed video. There's quite a nice number of puzzles under these TED Ed videos. I'll put the link to this. They have nicer pictures than I have, and their explanation is similar to what I'm going to say. But if you don't like my explanation, you might want to give a second try at this one here. And in any event, pause the video, and if you want to try it, come back and I'll explain it on the next slide. Okay, let's look at a solution to the puzzle. We have the configuration copied from the last slide. The responses go from the left down to the right, from taller to smaller. and they're only allowed collectively to make one mistake. And the trick is that A will say black if he sees an even number of black hats in front of him, and he'll say gray if he sees an odd number of black hats in front of them. All the other participants will be able to deduce the color of their hat and say it based on the response from A. So A will start by saying gray since he sees 5 black hats, which is odd. Now everyone else, including A, knows there's an odd number of hats collectively from B to J. B, knowing that, and also seeing 5 black hats in front of him, will conclude that his hat has to be gray. If it was black, then A would have seen an even number. That's not the case. And then C knows that B's hat is gray, and he knows there's 5 black hats in front of him. So again, if his hat was black, A would have incorrectly stated gray. In other words, he would have had to indicate even in that case, but he didn't. So C knows his hat must be gray. Then D comes along, and D sees 4 black hats in front of her, and she knows the 2 hats behind her are gray, excluding A's hat, which we don't care about anymore. So in order for there to be an odd number in this collection, her hat has to be black. And it works that way down the line. We can just pick one. Let's just pick one more. Let's pick H. So at this point, H knows exactly what the colors are behind him, and only the color of hats behind him, and then for each person. So H knows that B to G got their colors correct, and he knows in particular there's 2 black hats behind him. He knows there's an odd number of black hats from B to J, and he sees 2 in front of him, and he knows there's 2 behind him. So he concludes his hat has to be black. So we could do this for 100 people. We can use the same logic, and everyone except for the first one is guaranteed to get it right. And you can just verify the logic by going anywhere in your list. Let's say there really is 100 people here. Then this person in the list would know the exact color of the hats when the person's behind him or her, and would know, of course, the exact color of the hats in front of him or her, and also know whether there's an even or odd number of black hats. And with that information, you can just decide whether your hat needs to be black or gray. So that's the trick. You have a 50% chance of getting them all right because of the guess by A, but you have a 100% chance of getting 9 out of, or only missing 1, independent of how many people there are there. And I think it's a pretty clever solution. What wasn't my idea? I didn't make up the puzzle, and I didn't get the solution, but I'm just explaining it here. So we'll look at one more on the next slide, and I'll get you started on that, and then I'll leave you to work through the logic on completing the puzzle on the next slide. So here's a puzzle for you to try. It's the same conditions, except I've changed the color of the hats around a little bit. So I'll get you started. A looks across in front, and A sees 1, 2, 4 black hats. So that means there's an even number, and A will say black to indicate an even number of black hats. So from B to J, all know that there's an even number of black hats, excluding A, which we don't care about anymore. And B will look forward and see that there's 4 black hats, so that's even. His hat couldn't be black because then A would have indicated an odd number of black hats. So B knows his hat is gray. Let's just do one more in the middle. Let's take G. So, and assume that everyone's worked correctly from using the logic described here. So G would know the colors on the hats from B, C, D, E, and F. So G knows there's two black hats behind her, and there's two black hats in front of her, which is even. She knows that A said there was an even number, or indicated there was an even number of black hats in front of A. So G knows that there's an even number of black hats from B to J. And since G is aware of these four black hats, G knows her hat cannot be black. It has to be gray in order to preserve the even number of black hats that she sees. Okay, so you might want to try it for just any one of these. Try the logic for E, assuming that the three behind it were deduced correctly, and knowing that E can see it in front of him or her, and work through the logic there. There's something known as the moving sofa problem, and the problem is shown here, or at least a version of it on the right. The idea is that you have a 1 unit width here, and also a width going down. That could be a yard or a foot. I guess it would probably be a yard if you're talking about, or a meter if you're talking about a sofa. That's not really important. It's just that you have 1 unit. And this was a unsolved problem for a very long time. In terms of a personal story, I saw this in a high school geometry book. They weren't expecting the students to solve this, but it was just listed there as they had some like unsolved problems. And this is in the early 70s. And that problem always stuck in my head. I was wondering if anyone ever had solved it. And I recently saw this in a news article that someone, Joseph Gerver, has a solution which people think, it hasn't been completely verified, but people think he has the best solution, the optimal solution, and it's 2.2195 is the biggest area of a sofa going about the curve here, and I guess this is sort of the shape of the sofa. There's other versions of this, but it's the number is what's important. So this is the thought to be the largest area, and he published the result in November 2024. So I'm recording that. That's just a couple of months ago, and it was posted in Arvix. That's a place where different scientists, mathematicians publish articles before they go into formal journals. And the idea is they get some comments. Some people may knock it down. Other people may say, "Oh, this looks correct." And then, if everybody seems to think it's correct, or if there's some minor mistakes to be corrected, then the paper's updated and sent to a formal journal. So that's the state of affairs as I'm recording this concerning this problem here. If you're interested, you can go to the Wikipedia article I have listed here. It's just, the name of the article is Moving Sofa Problem. In an earlier lesson, we talked about Kaprekar's process on a 4-digit number. If you recall, we took a 4-digit number and we put the digits in descending order and then ascending order, and we subtracted them, and then we did it again and again, and we saw that we always converged to the same number after at most 7 steps. And then I left as an exercise to find the number to which you converge for only 3 digits, and I didn't talk at all about whether it works if there's something similar for 5 digits. And I at the time, actually, when I recorded the lesson, I didn't know if there was or not. So I looked around and I found something here. I put a reference. I'll give you the link also in the description of this video, but I found something on Proof Wiki that talked about the process, Kapprekar's process for 5-digit numbers. The word mistake here is because I guess there was something published on Proof Wiki that had a mistake, and then this is the updated version. So there is something similar. It doesn't converge to one number, but what happens is if you do this process of you taking a 5-digit number and then putting it in descending and ascending order, the digits that is, and then subtracting, you run into these different cycles. And there's 3 different cycles here. So once you got into the cycle, you keep circling back, and you basically stay in this cycle. You can't generate any numbers other than what's in the cycle once you enter into it. So it's not a convergence to one single number, but a convergence to a cycle or a set of several numbers that when you perform the process, you come back to the number you started with. So we'll do an example, or actually I'll give you a problem to work on, then I'll show you the answer on the next slide. So if you take this and then order it as 2, 2, 2, 1, 1, and then subtract 1, 1, 2, 2, and then keep doing that, you'll see that you fall into one of these 3 cycles here. And again, we'll talk about that on the next slide. I didn't investigate whether this works for 6 or 7 or 8 digits. I assume either it doesn't work at all, or if it does work, it's probably this type of solution where there's multiple cycles that you can run into and kind of get stuck in the cycle. So let's see what this looks like for a particular example, which I'll do on the next slide. We have our solution here to the problem from the last slide, 1, 1, 2, 2, 2. I'll just talk through some of the numbers here just to make sure you understand how these are being computed. So we take the number we're starting with, and we write this in descending order. It would be 2, 2, 2, 1, 1, and we subtract 1, 1, 2, 2, 2 from it, and we get 1, 0, 9, 8, 9. Then we put that in descending order from highest to lowest, so it would be 9, 9, 8, 1, 0, and then we subtract 0, 1, 8, 9, 9, and we get this number here. Then we again put it in a descending and ascending order and subtract, so we get 9, 9, 7, 1, 1, and we subtract from that 1, 1, 7, 9, 9, and we get this number, and we continue until we hit this number here, 6, 2, 9, 6, 4, and then we notice that that's one of the numbers in one of the cycles. So the 3rd cycle here, I just recopied this from the previous slide. So that's our solution. It's this converges, and it converges into the 3rd cycle here. What I haven't been able to find out is how many steps these for 5 we get convergence. I know for 4 the number is 7, that we always converge in less than 7 steps, but for 5 I wasn't able to find anything saying any theorem or document or article saying how many steps at the maximum it would take for any 5-digit number to converge to one of these 3 cycles. So if you please put a comment in the next to this video. So I found out a little bit more information. There's a website in France. I put the link here, and I'll also put it in the description to this video so you can just click on it. But it's a very nice page that they have, and it actually will compute the process for 5-digit numbers, 4-digit numbers, 3-digit numbers, actually even 6, 7, 8. It goes up to larger numbers of digits, and you'll see on the left-hand side of the page the calculations. So you can check, like I'll give you a number to work on, say 1, 2, 3, 4, 9. You can try that on this website, and you'll see which one of these cycles it converges on. So there's also cycles for larger numbers of digits, and they list them there. They don't give you the cycle, they just give you one number in the cycle, and of course if you go through the trouble of working with it, you'll find the other numbers in the cycle. But apparently the algorithm has the same type of convergence for higher numbers than 5 numbers of digits for 6, 7, 8. They show, as I say, several of them. And the way the convergence is into a cycle as opposed to just one single number the way we had for 3 digits and 4 digits. So have a look at this page and try out a few different numbers and just convince yourself that they always converge. Now the one caveat is that you have to have at least 2 numbers different. So if you took 1 1 1 1 1, then of course when you start you're just going to get 0 and then 0. I guess you could say it converges, but it's converging to the fixed point 0, which isn't particularly interesting. Okay, so that's all I know about Kaprekar's algorithm. If you know more, please put a comment on this video. Thanks. We have another puzzle called the Pirate's Treasure Puzzle. Again, I saw this on the internet. I've seen this a few times. I'm not sure why there's either prisoners or some form of criminals that are the topic of puzzles, but again, it's not my idea, so I'll just play along with this. So we have 5 pirates, all men except the captain, and they're of different ranks from 1 to 5, 5 being the lowest rank. So the captain is the highest ranked person, and they have a stolen treasure of 100 gold coins, which they need to split amongst themselves. The captain, pirate number 1, she'll make the first proposal on how the coins would be divided, and then they'll proceed down to, if that's not accepted, they'll go to pirate number 2 and pirate number 3, all the way down to pirate number 5. There's certain rules that the pirates abide by, no matter what. Even though they're criminals, they have some rules that they all abide by, and that's what I'll talk about here. That's what you need to work with in order to solve this puzzle. So all the pirates, including the captain, vote for or against the initial proposal from the captain. If 50% or more of the pirates vote for the proposal, the coins will be shared as specified by the captain. Otherwise, the captain is thrown overboard, and the process is repeated with the remaining pirates, according to rank, until agreement is reached. So the 50% rule follows all the way through. You need to just get half of the votes. And of course, if the first 4 get thrown overboard, then the last pirate, the lowest ranking pirate, would vote for whatever he proposes. I mean, there's nobody there to monitor at that point, but effectively the last pirate would get all the coins if it comes to that. Further, if a pirate can get the same number of coins by voting for or against the proposal, he or she will vote against the proposal. Okay, so that's important to keep in mind when you solve this. Assume all the pirates are rational and seek the highest number of coins and do not wish to be thrown overboard. What is the outcome of the process? Okay, so I'll give you the answer on the next couple of slides, and you may want to pause here and work on the puzzle. I'll give you a hint. You may want to work backwards and start from what would the pirate rank number 5, the lowest ranked pirate, what would that pirate do if everything came down to him? In other words, if all the first 4 were thrown overboard, and then think about what would the number 4 do if the first 3 were thrown overboard, and then continue working backwards and see and assuming that everybody knows that everybody else is thinking rationally in terms of what's the best option for them, and you should be able to find a solution for the captain to propose first. All right, so we have a solution. I'll talk through it. Actually, it takes quite a few slides to go through all this, but I basically followed the hint that I gave you. So pirate number 5, that's the lowest ranking one, only gets a chance to make a proposal if pirates 1 to 4 have all made proposals that have been rejected and thus thrown overboard. And clearly Pirate 5 would be the only pirate left on board and has no choice but to offer the 100 coins to himself, and of course he accepts it. Again, as I mentioned, there's no one to monitor it at this point, so it's almost, the process is already over. Once pirate number 4 is thrown over, 5 just takes all the 100 coins. So working back one step from there, what would pirate 4 do if 1 to 3 has been thrown overboard? And keeping in mind that you only need to get 50% of the votes to win the your proposal. So it's the process is only slightly more complicated for pirate number 4. He knows that he only needs 50%, and he's going to vote for his proposal. So he proposes that he gets all the 100 coins, and he votes for his proposal. Pirate number 5 votes against it, but it doesn't make any difference. He still gets 50% of the vote. And so in that case, when the first 3 pirates are thrown overboard, pirate number 4 gets all the 100 coins. And again, the pirates keep to their procedure. Even though they're otherwise dishonorable, they do keep to their procedure. So pirate 5 has no option here. He's going to get nothing in this case. So of course, pirate number 5 would not like to see it come to this point where just 4 and 5 are left. He knows you'll get nothing in that case. So keep that in mind when you move back to the next case, which I'll talk about on the next slide. Things get a little bit more complicated, but not too bad for the case where pirates number 1 and 2 have been thrown overboard, and pirates 3, 4, and 5 are still present. So at this point, it's up to pirate 3 to make a proposal. He doesn't want to get thrown overboard, of course. So if he proposed to take all 100 coins, pirates 4 and 5 would vote against that, and he would lose the vote 2-1, and then be thrown overboard, and then it would go to pirate number 4. And we know what happens there. Pirate 4 would take all the money. So the trick is for pirate 3 to offer something to pirate 5, so that pirate 5 does better than 0. And it's not a great offer to pirate 5, but again, they all follow these rules. So what happens is pirate 3 offers 1 gold coin to pirate number 5, and pirate number 5 knows if he rejects that, he's going to get pirate number 4 taking 100 of all of the coins. So in that case, the proposal from pirate number 3 is 99 for himself, 1 for pirate number 5, and pirate number 5 will vote for it. So the vote will be 2-1, and pirate number 4 will get 0 in that case. So pirate number 4, keep this in mind, does not like this option here where it reverts to pirate number 3 to make the decision, because he gets 0 in that case. All right, so let's peel it back one more. Talk about that on the next slide. So we move back one step here. We assume pirate number 1 has been ejected from the ship, and pirate 2 needs to decide on an offer at this point. Of course, 3, 4, and 5 are still on board. So we have the same problem if pirate 2 offers all the coins to himself in his proposal. The other 3 are going to reject that, so that's not a possibility. One possibility is that pirate number 5 is only going to get 1 coin in the event pirate number 2 gets thrown overboard. In other words, if we revert back to the case from the previous slide. So pirate 2 could offer 2 coins to pirate number 5, and that would be a better offer for pirate number 5, and he would accept that, and then pirate 2 would get 98. Pirate 5 would get 2, and they would both vote to accept the proposal from pirate 2, and you only need 50%. And 3 and 4 would vote against it, but that's okay. So that's one option, but pirate 2 could do even a little bit better by offering 1 coin to pirate number 4, since 4 would get 0 coins if pirate 2 is rejected or thrown off of the boat, and which is what happens in the previous slide. So in this case, just pirate number 2 says, I'll take 99, and I'll offer one coin to pirate number 4, and pirate number 4 knows he's going to get even worse if he rejects this, so he accepts the offer. And so you have 2 and 4 voting yes, and the other 2 no, and that would be how it's settled. So knowing all of this, the reasoning behind all of this, we come back to the captain, and she's actually going to be able to take the lion's share of the coins with her solution, which I'll talk about on the next slide. So finally, we're back to the starting point, the pirate captain, pirate number 1. So she needs 3 pirates, including herself, to accept her offer, or in other words, she needs 2 of the other pirates to accept her offer, or she's going to get ejected, and then we revert back to the case of pirate number 2. But she can prevent that from happening. If the captain gets ejected, then pirates number 3 and 5 know that they can be forced to take 0. We just went through that in the previous slide. So the captain only needs to offer 1 coin to pirate 3, 1 coin to pirate 5, and she'll get their votes, because if they reject it, we go back to pirate number 2, and 3 and 5 get 0 in that case. So that's what she does. The captain proposes 98 for herself, 1 for number 3, 1 for pirate number 5, and she wins by a 3-2 vote, and that's the solution. So this is known as a Nash equilibrium, named after John Nash. You may have heard of him. There was a movie a few years back about him. I think it was called A Beautiful Mind. And the Nash equilibrium is a situation where no player can gain by changing their strategy while the other players hold their strategies fixed. And if you think through that, this fits to this definition here. On the next slide, I know this is a lot to bring in, so on the next slide I'm going to kind of summarize the process in one table, and that may help make it a little bit easier to understand. So to summarize everything in one table that I discussed in the last several slides, let's start from the bottom. So we have pirate 5 remaining. So in other words, the first 4 have been ejected, and of course pirate 5 would take the full 100. And then we had the case where the first 3 were ejected, and pirate number 4 would take the full 100, because he knows that you only need a 50% vote, and he's going to vote for his proposal, and pirate 5 loses out there. Then we move back to pirate 3, where pirate 1 and 2 have been ejected, and pirate 3 knows that if he offers 1 coin to pirate number 5, pirate number 5 is going to accept, because if pirate 5 rejects, then it comes down to this case, and pirate number 5 gets 0. So that's what happens here. Then pirate number 2, assuming that pirate number 1 has been ejected, makes a proposal, and he knows that if his proposal gets rejected, it goes to this case here, where 3 gets nothing. So he knows that if he just offers pirate number 3, where pirate number 4 gets nothing, and he knows that if, in this case here, and so he knows if he offers pirate number 4 1 coin, pirate number 4 doesn't want things to revert to this case here, so pirate number 4 would accept, and then you have this solution being carried out. And finally, pirate number 1, the captain, she looks at the situation, and she knows that if her offer gets rejected, then 3 and 5 get 0, because of what pirate number 2 would do. And so she realizes she can just give 1 coin to 3, 1 coin to pirate 5, and they'll accept because otherwise they're going to get 0, and then she'll win by a 3-2 vote, and she'll get 98 of the gold coins. So, a little bit unusual because of the conditions that are put here where the pirates follow the rules exactly, but given those rules, it's a rather interesting logic puzzle because the pirate going first, the captain, can actually get 98 out of the 100 coins.